talk about a few things here. So when we were here yesterday, we were talking about finding limits algebraically, right? Or analytically, correct? Then once we kind of practiced that, which is we're going to finish practicing on that after I get done talking about continuity. Did we finish it or not? Yeah.
This
Yeah.
one, no.
Oh,
We did a decent bit of it.
We almost finished it, didn't we? Okay, so we're going to talk then, we were talking about that. Now, then we moved on to continuity. Remember that we had continuity here where we've got discontinuities that we can look at. We have a hole, right? We have an asymptote that we're talking about. We have jumps that we're talking about, right? Those are all things that we can look at when we're talking about continuity. If I wanted to check, right? If I wanted to check for continuity algebraically, then I could, then I have to work on this checklist that I have here, right? So in order for us to have continuous function, the function must be defined at that, at A, the limit must exist at A, and the function and the limit would have to be the same thing. That was our checklist we were working on. All right, then we talked about finding it algebraically, right? Determining whether it was continuous or not by kind of walking through those checklists. And then the last question that we answered before, or the last problem we were working on before we left, had to do with this similar type question here where we wanted to know what values would exclude it. So you were thinking asymptotes and holes and those types of things. So what we want to look at now is, okay, still kind of along the same vein, talking about things that are continuous. Remember we had this piecewise function here that was continuous. Okay, it was continuous, and although it did not exist when at x is equal to 0 for the second part of this function, it does exist in the first part of the function, right? So they kind of overlapped each other and they made it continuous. So what we're going to look at in these two examples here are I want to know what are the values that are going to make this piecewise function continuous here. I'm going to solve for these constants. That's what we're looking at. Find the constants a and b such that the function is continuous for the entire real line that we're looking at. All right, and what we have is our first function in this piecewise function, which is defined as a quadratic, let's say. And then I have a second function, which is going to be linear in nature, right? And if I were to kind of sketch, let's see if we can kind of sketch what this thing looks like. I know that I've got values at 1 and let's see, that would be at 3, 2, 3. So we would start here and move up in that direction as a curve. And then I have some sort of linear equation, which is going to be values less than 1. So it's going to be similar in shape to the one that we were just looking at. I know I'm going to end up crossing the x-axis somewhere down here. I have an intercept at 4, I think. Somewhere down there. So what I'm kind of sketching out as my brain is trying to take hold here is what is the equation that is going to connect, right? What is going to be the equation that connects, I should say, this line, this green line, to that top line to make it continuous. So at this end point here, we know that the 2 points are connected, right? They have the same value, they have the same function value at that point. So let's use that as a launching point in what we're talking about. So when x is equal to 1, the function is equal to 3 times 1 squared, or in other words, 3. The function itself is equal to 3. So this is the intersection point, right? This equation here, ax minus 4, I don't know what a is, but that would also, since this is the value of the function at 1, that would also be the, what this linear equation would be equal to at 1, right? So we have the equation then, some constant a times x equals 1 minus 4 is equal to that function value of 3. So I'm using the same point for x, 1, and the function value of 3, right? 1 comma 3, and I'm replacing it into that linear equation that you see there. Getting rid of all of the unknowns except the value of that a, or except a, which is what I want to solve for. So in other words, I have a is equal to, when I add 4 to the other side, a would be equal to 7. There's only one unknown in that particular equation, or in that particular piecewise function, a. In the second one, we have 3 pieces, don't we? Well, we have 3 pieces to the function, and there are 2 unknowns in that. So this function, let's kind of look at what that function would look like really fast. So at -1, when x is equal to -1, the function itself is equal to 2. When x is equal to +3, the function itself is equal to -2. -2. What I'm trying to solve for is, what is that equation right there? Okay. So we handle this, we have 2 unknowns, don't I? I have an a and a b for constants that I'm trying to solve for. And whenever I have 2 unknowns, how many equations do I need to have to solve for that? 2, right? For every unknown, you have to have that same number of equations. So if we start here with this equation here, and we use the same idea that when the function is, when x is equal to -1, the function is equal to 2. So in other words, I'm going to take that and I'm going to say a times -1 plus b must be equal to 2. Because this blue line here, that second equation, has to also at -1 be equal to 2. Then we're going to do the same thing here to find a second equation. So when x is equal to 3, the function ax plus b must be equal to -2. Now I've got 2 equations with 2 unknowns, right? All right, so I'm going to simplify these. I end up with 3a plus b is equal to -2. This one I have -a plus b is equal to 2. Now you have 2 ways to solve a system of equations. You can either use substitution, or I can use addition or elimination, right? That combination right there. So I'm just going to bring this down here, and I'm going to say -a plus b is equal to +2. And if I change the second equation, if I multiply the second equation by a -1, then I would change every sign in there. And that way, when I add them together, I eliminate b, and I end up with 4a is equal to a -4, or a is equal to -1. Does everybody remember how to solve systems of equations? You either do substitution or you do elimination, addition. The addition elimination method is what I just did right there. We're adding together to eliminate the variable. Now that I know what a is, I need to plug that back in to find out what b is. So I've got 3 times -1 plus b is equal to -2. -4 plus b is equal to -2. Or b is equal to a +2. Did we do that right? Does that look right? That's -3, not negative 3. Let's try that again. Y'all awake and looking at my math yet? Negative 3 plus b is equal to negative 2. B has to be equal to a positive 1. Is that correct now? Yeah, that's correct. Okay. So we found what the constants would be then to make this thing continuous. That was the charge. All right, Armando, do you see what I did for my numbers?
Yeah.
Yeah?
Yes.
Okay. All right, question?
So you close the negative. Okay, so where did the come from? 3 times. N equals -1. 3a plus b was an equation.
3a plus b is equal to negative 2 is one of my other equations. I just plugged in negative 1 into one of the 2 equations,
Oh, okay.
right? You use when you solve 2 equations, solve it once and then you plug that number back in and substitute to find the other one.
Okay.
Okay? Questions on that? No? All right. So let's look at these 2 concepts right here for just a moment. What do you notice about this function on the left? It's a half a circle, right? It's a half a circle, all right? And you can see the function at the top is the square root of 9 minus x squared, right? So that's the function that we're looking at there. Now we can see that this function is continuous if we wanted to talk about it inside of these values here, right? It's continuous on that inside of that function, okay? And when we think about continuous functions, okay, sometimes if we're looking at a function that looks like this, it's helpful to take the limit, right? Is it continuous from the left versus is it continuous from the right? Okay, because I guess a better way to approach this as we're talking about it is, if I'm interested in this point here, which would be -3, and I wanted to know what is the limit as the function approaches -3 from the left. Well, it doesn't exist, does it? Right? And the limit as the function approaches -3 from the right, it does exist, right? Okay. So, and we have a similar issue if we're talking about this 3 that's over here on the opposite side. So what we're going to look at here is if we can say, if we want to talk about a function being continuous, let's look at it in terms of limits, one-sided limits. So we know that this function is defined from -3 to +3. All right. And if I wanted to talk about then the limit as x approaches -3 from the right, what is that value? What is the limit as x approaches -3 of this function from the right? The function is getting closer and closer to 0, correct? Okay, let's talk about then the limit as x approaches +3 from the left, from the negative side, and what do we have here? 0, okay? So because we're kind of restricting what we're looking at, okay, and we're staying within this constrained bounds between negative and +3, we're staying within the domain of the function. If the limit exists within that domain, then we can say the function is actually continuous. All right, it's kind of a workaround, I would say, for some of these. So we can actually talk about this function being continuous because we are taking the limits, one-sided limits though, between what is defined already from the domain. Okay. Now, another one that you kind of see, I don't know, not very often, maybe sometimes you do, is this step function here. If I wanted to talk about whether or not this function is continuous versus not, it's kind of straightforward, but it is something that you would see. How would you define this function here? Is this continuous or not? It's not continuous, it's discontinuous, right? We keep jumping from one to the next, okay? Another way to look at this, so we know that this is discontinuous. We can also kind of look at this and say, okay, well, if I wanted to do a similar process here, if I wanted to say, what is the limit of the function as x approaches 0 from the left? So as I get closer and closer to 0 from the left, the function value is getting closer and closer to -1, right? Okay. If I wanted to take, well, they're not the same anyway. I would just say that I'm not even going to go with that one. I'm going to say that it's discontinuous. You can look at it being discontinuous because we've got these jumps in here anyway. The greatest integer, that's what this is called. Okay, the last thing that we want to lead then to would be the intermediate value theorem. The intermediate value theorem is useful for us when we start taking derivatives in the next section. And we can use this idea of continuity to be able to talk about roots to a function. So the idea here says that if we have a continuous, if f is a continuous function on a closed interval, and the function values are not equal, so it wouldn't be the same point, in other words, and you have k, which is in between my two function values, then in other words, there must be some value in between this interval. All the intermediate value theorem, one of the things that the intermediate value theorem tells us is we are basically guaranteed a root. If we're looking at this closed interval here, we're going to have some function value which falls on that function. And we use it, in other words, to find roots. Let me show you how that looks. I want to be able to use the intermediate value theorem to show that the function x cubed plus 2x minus 1 does indeed have a 0 on the closed interval between 0 and 1. So the first thing that you have to do when you're thinking about this is you have to determine whether or not the function is continuous. Is the function continuous? This is the function we're looking at here. We've talked about ways that we can look at it yesterday. One of the easiest ways to look at this is what type of a function is this? If I had to name or classify this function.
Polynomial.
And polynomials are all continuous, aren't they? That was a good one. So yes, it is continuous because it's a polynomial. Then we need to look at the endpoints. All right, we're going to check the endpoints and determine whether or not the endpoints are positive or negative. The endpoints on this closed interval, that's the endpoints we're referring to. Okay, so now we need to address the endpoints. By that, we're going to take the function and evaluate the function at the endpoints. So for f of 0, we would have 0 cubed plus 2 times 0 minus 1, or in other words, a -1. And at f of 1, we have 1 cubed plus 2 times 1 minus 1. 1 plus 2 would be 3 minus 1 would be 2. So what this says is if I want to only look at the portion of this function, right, that has x values between 0 and 1, where is the function at when x is equal to 0? Is it above the graph or below the graph? Okay, so here we can see it's below because that function value was negative, right? We did a bunch of this in our polynomial section. Here at 1, the function is positive or negative? Positive or above the graph, right? So in other words, if I have 0 and 1, and the function here at 0 is below the graph, and the function at 1 is above the graph, in order to get there, I have to cross the x-axis, don't I? So I'm guaranteed then a root on this interval. That's all I was asking. That's all the intermediate value theorem is telling me. All right? So there must be a 0, I don't know where it is right now, between 0 and 1. Because if we are talking about a closed interval and I'm only looking at the left-hand side being 0 and the right-hand side being 1, the function is below the graph at 0, but above the graph at 1, somewhere in between, it has to cross. And that's all we were asking with the intermediate value theorem that we're looking at, okay? And it just is a way for us to kind of use and expand on this idea of continuity. All right, because that's the section that we're talking about, is continuity. Okay. Let me put these up here. These are the problems that I would like for you to work on. Can you all see those? Yes?
Yes.
Okay, so for those problems there, I want you 1 through 6. For 1 through 6, I want you to, it says, I want to know what the limit is as the function as you approach c from the left, the right, and then just the limit, right? As x approaches c. That's what that says at the top.
Oh, that's what C is.
Yeah, it tells us what c is on each one of those pictures. So just write those on your paper, your results, right? The results of those. Okay? Did you get those answered? No? I'm gonna move it up a little anyway. You got at least 1 and 2 done, right? Yeah? What I want to know is, on 41 through 49, those that are circled right there, I want you to determine, how did I state it in the notes? I want you to determine where find the values of x that would make this not continuous. For 41 through 49, find the values of x that would cause this to not be continuous. 41 through 49? I want to know what number, if any, causes that to be discontinuous. True, but remember, she's there. No. There isn't. So it is. Algebraically, there isn't a number that's positive. And what do we know, just thinking back, we're gonna think the numerator. I would say that it has to be but it's still gonna be the across the thing. That's the thing, that's the crazy thing now. I'm here, I have to be on that. Because even though I believe that it doesn't have to do with it, according to our rules. We can cross this word on that. Crazy. So there's no, how, is that what you said? Because asymptotes, asymptotes are really more about the end behavior. So just like our noisy oscillating functions that have a bunch of noise right there at the origin, not necessarily about what's happening at the origin. What happens as the noise part, which is really what an asymptote is going to be. The rules for those, we're going to talk about this. The next thing is the limit as x approaches infinity. How are y'all doing? Yeah? Check your answers with your neighbors? Yeah? So you're interested in, if I want to know what makes a number and what makes them not continuous, then that's when, especially all of them are rational functions. Right? I'm interested in if they're not. Or if they're or is there a denominator? Where does the denominator? The denominator equal to 0. That would give me a vertical. Did you?
Yeah.
A whole would give me an aspect. I mean, a whole would give me no.
Yeah.
And the nice thing about that is I would always, it's always helpful to just always do the calculator.
Yeah.
Can you look at it and ask you to figure out.
So you try. Oh, it's 0 intersection.
So for this, we are interested in, are there any holes that are occurring? Is there any vertical aspects, right? No, right?
Yeah.
So then we would assume that it's going to be continuous, right?
Yeah.
If you are connected to the internet,
Yeah.
what does
Yeah. The ones. That's right.
So we're really looking for more horizontal asymptotes, right? No, excuse me, not looking for horizontal asymptotes. That's what we're not looking for. We're really almost looking for vertical asymptotes on these, right? And holes, vertical asymptotes and holes. And always feel like you can throw this into the calculator to see what it looks like. Does your conclusion support your algebra? Yes. The hole, so that makes it discontinuous. And it has a vertical asymptote.
It has a horizontal.
So what are you deciding when you're out? Do you make a conclusion based on anything? So I don't know what do you want to do? Because what? So you would therefore, so it would be discontinuous, right? A non-removable discontinuous.
Are we just gonna just do a circle one, or just 41?
Just the circled ones.
Do we need to specify if it's not non-removable?
I don't know. I'm trying to think about it. And I don't remember. Off the top of my head.
Sure.
I would want to know that it was a hole. Is it there was a discontinuity. Hole. That would be a removable discontinuity. Maybe you just hold this one. Because you're at least identifying that, right? That the whole is giving us the discontinuity.
But it's 45.
So is it continuous?
Well,
Because that's the question also.
Why would it?
The question is, give me the x variables that cause it to be discontinuous. Are there any x variables? Are there any x values that cause it to be discontinuous? No, right? So it would be continuous. What do we think? There's a hole. And no, you just know that there's a hole. Yeah.
Top one.
So it's just. What does it look like? Yeah, that's it, right? And it does have a horizontal aspect, doesn't it? Strangely enough, we cropped it, didn't we?
Yeah.
But that's okay.
How I was looking at it. You look at it.
After that first.
Negative.
You get X X times X. But it's not an asymptote, it's what?
Yeah, it's inside.
Okay.
So 3 over negative. Because it's lower than 7. It's positive. And when it's lower.
What do you think?
Okay, so 45, you
Yeah.
can't factor that out. So, and then when we set it at 0.
Anything?
Right, so it's, did you graph it? Is that it right there?
It looked like that when I first got it.
You don't even have to put the Y.
I actually got one more. I think I actually got the right answer.
I mean,
So it's.
It looked like that.
oh, it's got a curve in there, doesn't it? And it's curvy, curvy, right? Yeah. It just looks like a jagged line that way.
It looked like that.
The scale? Okay. Okay. You want to go over the answers? Or you need another minute or so?
I'm good.
Oh, okay. I'm gonna go over the answers. So for 1, 2, and 3, this is what I have written down. 1, 2, 3, 4, 5, 6. This is what I have written down. 3, 3, and 3 for 1. -2, -2, -2 for 1, for 2. So we would be continuous at both of those places. -3, or excuse me, 3, 3, and 3 on number 4. I guess I skipped. So the limits existed, but we were discontinuous for 3 and 4, were we not? Nope. Okay. 5. 3, 3 does not, 3, -3 does not exist for their limits, but we are discontinuous at x is equal to 2. Because we have a jump, right? I think on 6, 2, 0 does not exist, and discontinuous at x is equal to -1. Those are good questions for a quiz or a test, in that it's getting you to take the limit graphically from the left, from the right, and then the limit together, right? And your kind of rule of properties of limits, let's say, right, that they have to be the limit to the same number for the limit to exist. And then as well as telling me a little bit of information about continuous versus discontinuous. All right, so that's kind of the quiz questions that I would, and test question that I would look for on something like that. And then what quickly I was doing, 41, 43, 45, 47, 49. So I would encourage you again to throw these into the calculator just to kind of reinforce what you're doing, maybe give you some confidence about what you're doing, or if you are stuck, maybe you can look at the graph and see how you could go algebraically from there, right? So they should support each other. Okay. All right. Any questions over that? So what we're gonna talk about and then practice. Because you said you did all of those problems from our find the limit practice algebraically. You did all of them? I thought I stopped you, but I guess we did it all right then. Yeah? Okay, good. We got other stuff to practice today. Okay. We're going to talk about, and we'll split this lesson. So we're going to talk about types of limits. And what we're going to focus on today has to do with limits at infinity. Now, the difference between the two limits, you can see their pictures here, right? So when we think about this, we have limits at infinity. So in other words, our independent variable of x is increasing or decreasing without bound. Those are the asymptotes that we're thinking of, right? We are taking the limit as x gets increasingly larger. And those would be our asymptotes that we're thinking of. Limits at infinity says I'm going to go in the positive infinity direction, or I'm going to move in the negative infinity direction as x is approaching negative or positive infinity. Now, if we have here the function 1 over x squared, that's the graph of what you're seeing up there. And if we think about this function and we want to know what is happening to the function, what number is that function approaching? Because remember, the limit doesn't really care what happens at that number. We just want to know what happens as it gets closer to that number. So if we think about this for just a second, we say, okay, well, what is happening to the function? What is the number? What is the function getting close to as my denominator gets larger and larger and larger? So if I had, say, 1/3, and then I had maybe 1/5, and then I had maybe 1/10, right? 1/3 is 33% or 30.33. 1/5 is what, 0.2? 1/10 is 0.1. What's happening to those numbers? They're getting smaller and smaller and smaller, right? So in a fraction, as my number is getting incrementally larger, as the denominator is getting incrementally larger, the function, the limit of the function is getting smaller, isn't it? The limit of this is going to 0. And it's the same concept. It's a similar concept if we go backwards. Or in other words, if I go to negative infinity, I should say, right? That doesn't change the fact that it's going to 0. It's just we're now over 1 over -3 or 1 over -5. That's still -0.33 and -0.2 or -0.1, but it's still getting smaller and smaller and smaller, correct? So this is what we're thinking about when we talk about limits at infinity, okay? Limits going to infinity. And then when we come back to class tomorrow, we'll kind of finish up talking about what happens when I take an infinite limit, okay? So we'll just kind of leave that one there for right now, because we're going to focus on the limits at infinity. So when we look at limits at infinity, we're actually thinking about that end behavior, okay? And so we saw it just a second ago. Isaiah, what was that function? It was x over x squared plus 1?
Yeah.
Okay, and you all told me that that was a continuous function, and when you threw it in your graph, right, when you threw it in your graphing calculator, it looked like, no, what did it look like? Was it look like a sideways squirrel?
Flat line, like a S.
Oh, that's right, I remember now. Jumped up, didn't it? That's sort of what it did, kind of like that, right? Ish, it's an ish. Okay, so we know from our rules of our properties in rational functions that when the numerator is less than the denominator, right? Don't we have a horizontal asymptote at y is equal to 0? Yeah, vaguely remember that? So I have an asymptote here, but this function was continuous, okay? And it's actually okay to cross an asymptote because you see it happening, as you heard me probably explaining to Isaiah over there. When we think about horizontal asymptotes, what we're looking at is, what we want to consider is what is their end behavior? What is happening as it gets farther and farther and farther away from the middle, and not necessarily what it's doing at the middle? Remember, we had those oscillating functions for sine and cosine, and it had a bunch of noise around the origin, but it was at the end behavior that we had an asymptote. So that's what we're thinking about for limits to infinity. So In these cases, we are looking at horizontal, we can look at oblique as well. All right, and that's kind of what we're going to talk about when we think about the limit at infinity. So here's the formal definition of what it says. It says if f of x, the function, becomes arbitrarily close to some finite number, L, for all sufficiently large and positive x, then we can take the limit as the function approaches infinity, and the function would be equal to L. We're interested in coming up with, in essence, what we're going to say is as I take the limit to infinity, what number is my function approaching? It's what it's going to approach a number. So L is a number. Okay. And we do this in both directions. They don't have to approach, we're not going to get the same thing, right? We're not going to take something from the left and from the right of infinity and try to get it to be the same number. It may end up being the same number, but we're not doing, it's not the same as what we were doing before, where I'm taking the left and right hand limit of a constant. Okay, so let's look at these examples that we have here. This says, I want to find the limit as x approaches infinity of the function 2 plus 10 over x squared. Now, I don't know that you're going to do this all the time, but let's take this kind of piece by piece for just a second and see what it's looking like. This is saying, if we were to deconstruct this, the limit as x approaches infinity of 2 plus the limit as x approaches positive infinity, I should say, of 10 over x squared. Now again, we're not going to do this every time, but let's just see what's happening here. The limit of a constant is always the constant, right? Okay, so the limit as x approaches infinity of 2 is just simply 2. Now let's think about this limit here. The denominator is x squared. We're approaching positive infinity, right? So it's just getting larger and larger faster because it's a square, but it's still just getting larger and larger. When the denominator gets larger and larger, what happens to the value of this fraction? It goes to 0. That's right, it gets smaller. So we would have 2 plus 0, or in other words, 2. See how we approached a number? Is the limit as the function approaches infinity, as x approaches infinity, the function approaches 2. Okay. All right. Let's look at this next one. The limit as x approaches negative infinity of pi times the square root of 3 over x squared. Okay. So again, I'm going to deconstruct this for just a second. The limit as x approaches negative infinity of pi square roots of 3, right? And that's going to be times the limit as x approaches negative infinity of 1 over x squared. If I wanted to look at this in separate pieces, the numerator is just a constant, right? Or pi times the square root of 3 is just a constant, so that has to be pi square roots of 3, the limit. What happens to the second part over here, the 1 over x squared? What does it approach, we've said?
0.
0. So the limit of this is just 0. Now I could have come up with that same exact conclusion if I had just stayed with this limit right here, right? The numerator stays the same, but the denominator is getting closer and it's getting larger and larger. Therefore, the limit has to be equal to 0. Okay? You don't have to deconstruct it for me on a test. Okay? All right. How about this next one? Do what?
So does it?
It's not infinity. Okay. We have to think about, we know that the numerator is going to be a constant. What happens to the function 1 over e to the x as it gets larger and larger? So I'm going to think to myself, okay, 1 over e to the x is the same thing as e to the negative x, right? Okay. What happens when I have a negative here? We reflected it which direction? In other words, I guess the better way to say this is, I want everybody to put into their calculator. Let's just do this. Put into your calculator 1 over e to the x. It approaches 0, right? 1. So we have that function right there, right? So as our function is going to infinity, the denominator is getting smaller and smaller, right? It's going to, the function is going to go to 0, isn't it? 1 over x, 1 over e to the x is going to go to 0. Yeah? Okay. So when we are taking the limit of this, then we would say, okay, well, this is going to be the constant 3 times this guy right here, which is still just going to 0, or in other words, the limit of that function is going to go to 0. What do we think about this one?
It's one of those special limits, really.
It's a special one if the function, if x is going to 0. In this case, we're going to infinity. Okay? We can use the squeeze theorem on this. All right? We can use the squeeze theorem on this in a similar fashion to what we were doing before, right? So if I am taking this and I want to know what is happening to this function, let's say that, and I'm going to start with what I know. I know that sine x, the function, is between negative and positive 1 again. Now, I'm wanting to know what's happening to the function of sine x over x. So if I were to divide, instead of multiply this time, every term in there by x, I end up with a middle that's what I want, right? I end up with the middle part of what I want. So now if we look at this using the squeeze theorem, I want to know what is the limit as x approaches infinity of negative 1 over x. What's that limit? What's the limit as x approaches infinity of 1 over x?
0.
0. Very good. Okay. What's the limit as x approaches infinity of positive 1 over x?
0.
Still 0, right? So if the limit on the left is 0 and the limit on the right is 0, then by default, by the squeeze theorem, the limit as x approaches infinity of sine x over x must also be equal to 0. Right? It's the same thing that we did the other day, only instead of me multiplying through by x, this time I needed to divide everything in there by x. All right, to kind of manipulate that formula that we were looking at. Okay, so that is equal to 0. So we have this idea, right, that we're kind of taking the limit as x grows unbounded. Sometimes it's not very easy to figure those values out. Polynomials are easy to do. But rationals become a little bit more involved. The way that we handle this is we are going to multiply the numerator and the denominator by 1 over the highest power of the denominator. Okay, the highest power of the denominator. So let's look and see what happens when we are, what I'm talking about. The denominator, that's what I'm focusing on. The denominator is x squared, correct? It's already written in descending order, so it's x squared. So I am going to multiply both top and bottom by 1 over x squared. So when I do that, I'm taking the limit as x approaches positive infinity. And in the numerator, 3x divided by x squared is just 3 over x now, isn't it? X over x squared reduces down by 1. Yes? Yeah? Okay. Plus 2 times 1 over x squared, well, that's just 2 over x squared. So I have these fractions in the numerator, but hold on. There's a reason why we're doing this. In the denominator, we have x squared over x squared, which is going to be 1 for the first term. The second term is just minus 1 over x squared. Does everybody see where I did those multiplication, where I did that from? Now, the idea behind taking the limit here that we were using before is if I come in and look at each of these components separately, here, 3 over x, what happens to that value as x approaches positive infinity? That's going to be 0, right? Because the denominator is getting incrementally larger. What happens to the next term up there? 0. The denominator, I have 1, right? Here in the first term, minus 0. So 0 over 1 would just be 0. In other words, the limit, as this thing gets larger and larger, as x approaches infinity, is just 0. Now, this is, well, we'll come back to that in just a second. Okay, so that's what we do. That's the idea behind a rational function. You're going to multiply top and bottom by the highest power there. Okay?
Highest power of the denominator.
Highest power in the denominator. Yes, sir. Thank you. Okay? So let's look at the next one. What's the highest power in the denominator?
Specifically the denominator? or all?
Specifically the denominator. 4, right? X to the 4th. So I'm going to multiply top and bottom by 1 over x to the 4th. So that's the limit as x approaches infinity. What's the first term going to end up being? It's 40, right? Yes, thank you. It's going to go to negative infinity. 40. Plus, what happens? What happens for 4x squared? What does that happen to be? That's going to end up being what? 4 over x squared, right? Okay. X squared minus 1 over x to the 4th, right? Okay. And in the denominator, we end up with 10 plus 8 over x squared plus 1 over x to the 4th. So in the numerator, the limit of a constant is a constant. Plus 4 over x squared is going to be 0. Minus 1 over x to the 4th would be
0.
0 divided by 10 plus 0 plus 0, or in other words, 4. Okay? Let's look at this next one. So for this next one, what is the highest power of the denominator? X, right? So 1 over x, 1 over x. The limit as x approaches positive infinity, x squared minus 2 plus 1 over x divided by 2 plus 4 over x. X squared as x goes to infinity is just infinity, right? Plus 2 minus 0. Minus 2, sorry. Minus 2 plus 0. All over 2 plus 0. Well, infinity minus 2 is still infinity, right? Over 2 is still infinity. So it's infinity. Okay, you do the next one. Okay, did you get a negative infinity for that next one? Excuse me, did you get infinity for the next one? Mhm. Now, let's take a second and go back and think about our rules that we remembered from last couple of weeks ago, right? So we have rational functions, and let's talk about those horizontal asymptotes. So if I'm looking at the first one, the degree of the numerator was less than the degree of the denominator, right? We have a horizontal asymptote at y is equal to 0, correct? All right, and that's what this is saying. It's the same thing, right? Let's look at the next one. The degree of the numerator is equal to the degree of the denominator. Remember what happened there? When they were equal?
Oh, no.
Maybe this is what you were saying. It's the ratio of the coefficients, right? Yeah, sorry. Yeah, divide the coefficients 40 over 10, excuse me, which would be 4, right? And that was what we got, right? The limit as x approaches infinity is 4. Okay. What about the next one? The numerator is greater than the denominator by 2, right? We didn't end up having an asymptote there, did we? Right, so the function goes off to infinity. That's what this is saying right here. And in the last one, do you remember what happened there?
Long division.
Long division, we got a slant. We're still going to end up with the function going, as we go to infinity, the function itself is going to infinity as well. Okay? All right. let me give you this. And I want you to start working on this. To practice these limits. Okay, you can do all of them except 8, 9, and 10. And I'll stop you in a minute to finish that. Oh, I know what I want y'all to do. Okay, what I want y'all to do actually is, this is why I gave you this paper, is I want you all to, everybody get one? Yeah? Okay. I want y'all to find a place on the board, or I want you to find a place on the wall.
Well, we're supposed to, yeah, we're supposed to do the same thing.
I just didn't count one, right? Is that right?
You walked by as the secretary.
Okay, well, hold on to it for me, okay? All right, get up, find a spot. First one's to the board, get to use the board. Everybody else has to use paper. All right, since you're over here, you've got what? Several papers, several practice problems. All right, here you go. Here's paper. Refrigerator artwork right here, okay? That you can take home with you. Are these the extra guys? Riley, you can slap a piece of paper over here next to Zoe on the wall. Is there not enough? Oh, yeah, I thought you were going to get paper.
What are we doing?
All of them, it will, except 7, 8, 9, and 10. You can do 1 through 7. 1 through 7.